Good morning, girls. Today we will be discussing some problems on small oscillations. So this is something very important when you are really in desperate need to clear your CSER net exam. So this is an important topic in classical mechanics. So kindly pay attention to this class. So we have already discussed the concepts behind small oscillations and the conditions for stable equilibrium and unstable equilibrium. So hope you remember all those sessions and the important things that we have discussed. So we have to apply all that here in these problems. So the first problem is this a particle of unit mass moves in a potential v of x is equivalent to ax squared plus b by x squared, where a and b are positive constants. The angular frequency of small oscillation about the minimum of the potential is. We need to find the angular frequency. So the given potential is this. The first step is we need to find the first derivative of the given potential, which is dou v by dou x. So dou v by dou x is equivalent to 0. So this gives 2ax minus 2b by x cube is equivalent to 0, from which we have just found the value of x, which is b by a the whole power 1 by 4. And we all very well know the formula. Omega is equivalent to square root of k by m, since they have given as the particle of unit mass, m is equivalent to 1 and k is equivalent to dou squared v by dou x squared. So again we need to find the derivative. So that gives 2a plus 6b by x naught power 4. So here x naught represents a stable equilibrium point. So now we need to substitute the value of x naught here, which is b by a the whole power 1 by 4. So substituting the value of x naught in k gives the result as 8a. So at x is equivalent to x naught is equivalent to b by a the whole power 1 by 4, k is equivalent to 8a. So omega is equivalent to square root of k by m. So square root of 8a by 1. So that is equivalent to square root of 8a. So this is how we need to find the angular frequency for small oscillations. So the next step is the next problem deals with the conditions for stable equilibrium and unstable equilibrium. Just go through the question first. A particle is placed in the region with a potential v of x is equivalent to half k x squared minus lambda by 3 x cubed, where k and lambda is greater than 0. So now we have to find among the four options which one is right. The first option is x is equal to 0 and x is equivalent to k by lambda at the point of stable equilibrium. And the next option is x is equal to 0 is a point of stable equilibrium and x is equal to k by lambda is a point of unstable equilibrium. And the third option is both the points are of unstable equilibrium. And the fourth option is there is no points of stable or unstable equilibrium, and we just need to prove, or we just need to find among four options which one is the right option. So for which again we have to follow the same procedure. The first step is we need to find the derivative of the given potential, which is dou v by dou x. So that dou v by dou x gives two x values. One is x is equivalent to 0, another one is x is equivalent to k by lambda. So the next step is I need to find the derivative, second derivative, which is dou squared v by dou x squared. That gives k minus 2 lambda x. Now since we have two values of x, I need to substitute both the values of x in dou squared v by dou x squared. So at x is equivalent to 0, I'm getting a result, I'm getting a positive value for dou squared v by dou x squared. And for x is equivalent to k by lambda, I'm getting a negative value of dou squared v by dou x squared. So the positive value shows that it's a stable equilibrium and the negative value shows that it's an unstable equilibrium. So this clearly shows that option B is a correct option, that is x is equal to 0 is a point of stable equilibrium and x is equivalent to k by lambda is a point of unstable equilibrium. So hope you're following me, and if you have any clarifications you can just ask me. So now coming to the next problem, which is almost similar to this. Yes. So now you just Go to the question. Consider the motion of a classical particle in a one-dimensional double well potential. The potential is given, and if the particle is displaced infinitesimally from the minimum on the x-axis, then they have given four options. We need to find the right option. Again, it is the same procedure, which is where we need to find the first derivative of the given potential. Again, I'm getting two values of x. One is x is equivalent to 0, another one is x is equivalent to plus and minus root 2. Again, I need to find the second derivative, dou squared v by dou x squared. So I just need to substitute the values of both x values, which is x is equivalent to 0. So for x is equivalent to 0, I'm getting the dou squared v by dou x squared value as something negative because it is less than 0. So this is something unstable. And for the dou squared v by dou x squared at x is equivalent to plus and minus root 2, I'm getting a value which is equivalent to 4. This is something positive, which represents that it is a stable equilibrium point. So after substituting all that, so for the first value, I'm getting an unstable point, and for the second value of x, I'm getting a stable point. And to find the frequency, omega is equivalent to again the same formula, which is square root of k by m. K is nothing but dou squared v by dou x squared, which is 4, square root of 4 by 1, which is 2. So option B is the right answer, which is a particle will execute a simple harmonic motion with an angular frequency of omega is equivalent to 2. So yes, with this we can wind up. Thank you so much.